You know, so much of our super-fast digital world, from streaming movies to searching databases, a lot of it is running on one single, really elegant idea. It's the thing that lets us find exactly what we're looking for pretty much instantly.
I mean, really think about it. You've got this huge collection of stuff. We're talking millions of movies, billions of web pages, you name it. How on earth do you find that one specific thing you need without just getting totally lost in the noise?
And you've seen this happen, right? You start typing a movie title into Netflix, and boom, before you even finish the word, the result is right there. It feels like magic, but it's not. It's just a really, really clever algorithm doing its thing behind the scenes.
Okay, so let's get into the real problem here. When you're staring at this absolute ocean of content, how do you actually solve that search problem and make it feel like it happens in the blink of an eye?
Well, the most obvious way, the way we'd probably all think of first, is to just, start at the beginning and check every single thing one by one until you stumble upon what you're looking for. It's super straightforward, super simple. And it has a name, a linear search.
But just imagine trying to do that in a giant library with millions of books. To find one specific title, you'd have to literally pull every single book off the shelf. For a service like Netflix, with a massive catalog, this method isn't just slow, it's completely, utterly impractical. It would never work.
Thankfully, there is a much, much smarter way to do this. It's a strategy that computer scientists have a cool name for: divide and conquer.
And this brilliant solution is called binary search. And here's the genius of it. Instead of looking at things one by one, its whole game plan is to just chop the number of possibilities in half with every single guess.
Okay, but there is a catch. There's one really important rule. For binary search to work, your data has to be sorted first. I mean, think about a dictionary, right? The only reason it's easy to find a word is because it's already in alphabetical order. That's the whole secret.
So how does it actually work? It's so simple, it's beautiful. You just jump right into the middle of your sorted list. Then you ask one simple question. Is the thing I'm looking for before this point or after it? And depending on the answer, you just throw away the entire half you don't need. Gone. Then you just do the exact same thing again with what's left.
This visual really shows you how powerful that is. You start at the top, what's called the root, and with just one question, you either go left or right. And in doing so, you've just eliminated a massive chunk of data. Every single step, the problem just gets smaller and smaller, and it gets smaller really fast.
So, okay, it's obviously way faster than going one by one. We get that. But how do we actually describe how much faster it is in a way that's, scientific? Well, for that, we need to learn a new language, so to speak.
And this gets to a question that's right at the heart of computer science. How can we measure this stuff? How do we compare how good different solutions are, especially when the amount of data starts to get really, really big?
The answer is something called Big O notation. The easiest way to think about it is like a report card for algorithms. It doesn't care about seconds or minutes. It's all about describing how the work an algorithm has to do grows as you throw more data at it. And importantly, it usually looks at the worst-case scenario. It tells you how things will hold up when they get really tough.
And this graph tells you everything you need to know. See those lines that are just shooting up into the sky? Those are the inefficient algorithms. The work they have to do just explodes as you add more stuff. But now look for that line that's almost flat at the bottom, the one labeled O log n. That's binary search. Even when the data gets huge, its workload barely even moves. It's incredible.
So let's put this in perspective. Binary search's grade, its big O, is O log n, which we call logarithmic time. And it's called that because the number of steps it takes is all about how many times you can cut the data in half. And as you can see here, that is worlds better than linear, way better than quadratic, and it's not even on the same planet as the absolute disaster that is factorial time. It's just in a league of its own.
All right, I know, logarithmic speed sounds super abstract, but trust me, this is something you feel and use every single day. Let's connect the dots back to the real world.
That O log n efficiency, that's it. That's the magic ingredient. It's the reason why your digital life feels so snappy and responsive. It's what makes searching through a mountain of content feel like nothing.
And this idea, this logarithmic speed, it's not just for searching movies.
It is a cornerstone of all modern computing. It's what keeps huge databases from grinding to a halt. It's how your computer's file system works. It's what makes big data actually usable. It's really the invisible engine behind the instant world we just take for granted now. So, we've got this idea that's simple, elegant, and incredibly powerful. Sounds perfect, right? Well, here's the final and kind of fascinating twist to this story. As simple as the idea is, it is shockingly hard to get right in practice. There's this famous story about a computer scientist named John Bentley. He gave this exact problem, just writing a binary search, to a class full of professional programmers. And get this, a whopping 90% of them failed. They couldn't write a version that worked correctly, even after spending hours on it. They kept missing these tiny little details, these edge cases that would make the whole thing break. And you know what's even crazier? Bentley's own published version of the code had a bug in it that nobody found for 20 years. And the same exact bug was in the official Java programming language for nearly a decade. It's just an amazing reminder that just because an idea is simple and elegant doesn't mean it's easy to actually build perfectly.
It really makes you think, doesn't it? What other simple ideas like this are out there? What other bits of genius are hiding just beneath the surface, quietly running the incredibly complex technology that we depend on every single day?